So I'd like to introduce Joe Ferguson. He has his BS in computer engineering from the University of Idaho and is the lead software engineer in the Infrastructure Defense Division at Schweitzer Engineering Labs. And he's been on the system analytics team for over 10 years and focuses on protocol and software security. And then David Lowe, who is co-presenting this, graduated from the University of Idaho with a BS degree in electrical engineering with coursework focused on power systems. He currently works as an associate research engineer with the Power Group in Infrastructure Defense at Schweitzer Engineering Laboratories. So with that, I will just turn it right over to Joe and David and for their DNP3 usage and capabilities.
This is Joe Ferguson with Schweitzer Engineering Laboratories. I was asked to talk about DNP3 today, so my goal is going to be putting DNP3 in a context that provides all the background needed to do analysis on the protocol itself and understand the cybersecurity implications as they apply to ICS, SCADA, and applications of various communication protocols. So I will start with what is the DNP3 protocol and where did it come from? It's an IEC compliant protocol. It's compliant with the 6870 standards. It was created by a company called Westronic. It predates the IEC standard that it actually implements because it was in process at the time that the DNP3 protocol came out. So it was created essentially by this company that was doing protocol gateway work to do all these different translators between proprietary protocols. They recognized that there needed to be a central standard for doing this type of work. And they worked with the IEC community to implement this. But it is not the only protocol that can do SCADA and ICS style communication, right? There's a lot of different protocols out there. We're going to talk about Modbus later. I saw there's 61850, 6870 is related to it, right? You have BACnet, Profibus, Profinet. What are these things? Modbus is more of an ICS protocol. It's for doing individual data item transfer from device to device. Your 61850, 6870 are a little bit more SCADA protocols. I'm going to talk about what these mean. That's a big part of this presentation. BACnet is for building automation. Profibus and Profinet are Siemens proprietary. They're used by Siemens equipment to do the SCADA ICS style back and forth. And then of course we have DNP3. So I mentioned a couple of different words, SCADA, ICS. It's useful to explain what those mean, just so that you can have more meaningful conversations down the road, right? So operational technology, we're all familiar with this because of the plethora of IoT devices out there. You have your Internet of Things all talking out on the internet and doing various interactions with the physical world. And that physical interaction is what makes something an operational technology as opposed to an information technology. Your information technology, your IT stuff is servers. You have a computer talking to another computer, putting data into a database, displaying something on a screen, but not typically turning lights on and off, not typically turning a process on or off. So that's the distinction between OT and IT, is that in operational technology, you're interacting with the physical world in a real way. ICS is another sort of layer on the OT. In industrial control systems, you have a process you're controlling. So we're talking a factory, a refinery, right? You have some sort of process where you're trying to make a widget, to use the common example, and you have to control the process of making that widget. So you have a whole bunch of interconnected devices, and this one's measuring some element of the process, and this other device over here is controlling speed or a moving arm or a robot or something. And so you have these industrial control system devices communicating back and forth with each other, making sure that process carries on smoothly. But what if you have several different, let's say, assembly lines in a factory, or several factories, or a bunch of refineries, or a whole bunch of substations in the power grid, right? Now you have a whole bunch of different industrial control systems, and you might need visibility into those systems. And that's where SCADA comes in. You have supervisory control and data acquisition, where you have a concept of hierarchy. So you have some sort of human machine interface up at some top level. There's an engineer at a computer, and he has visibility into multiple processes. And that's typically the distinction that SCADA adds in, is you have not necessarily direct device-to-device control of a whole bunch of devices, but instead aggregated and carried up to some sort of human, so that they can make decisions on a process or multiple processes. So just to sort of summarize what makes something SCADA and ICS, their typical qualities are high availability. If you look into protocols, you're going to see confidentiality, integrity, and availability talked about a lot. It's often just called the CIA of the protocol, or CIA triad. But those are the typical metrics that you're going to compare and contrast different protocols with, is confidentiality, integrity, and availability. For SCADA and ICS, your availability is typically one of the highest requirements. You're gonna really make sure that your two devices are able to talk to each other with high reliability. And if they have to pass us a message twice, that would be bad, but you're assuming that these devices are probably linked directly to each other. There's less concern about the message being eavesdropped on, or other interference. The main concern is if I say, I need to turn this process off now because all of the widgets are falling on the floor off the end of the conveyor belt, I know that I'm going to send to the stop command, and that stop command is going to get through now before any more widgets fall on the floor. So you're directly controlling a process. You need to know that the message will get through and adjust the process correctly. The other thing that's huge is long-term reliability. In IT, it's pretty common to have to talk about applying updates. You're going to have servers turning on and off. You just shift the workload around, right? This is still a big problem, but it's something that you're used to. In a process, it's not uncommon to have devices on for years or decades without interruption. You can't necessarily take it down to apply an update weekly, right? That's just not something you can do. So it has to be on and reliable for years or decades at a time. Precise time is huge for many of these processes. You need to know that when I told you to do the thing, it was based on information that actually was from a second ago or a millisecond ago, microsecond even, right? So precise timing is huge. And then, of course, you're controlling and monitoring physical devices. This is not just a web page somewhere that's getting data input on it. And then another huge thing that makes these protocols unique is data mappings. And I'm going to talk about that a bit more later. But first off, I wanted to get into where you're going to see DNP3. Once again, this is used with field devices. So you're not going to see DNP3 communications on a typical Dell server in the wild, right? This is industrial use, automation use. You're going to see the term IED, which in this case means intelligent electronic device. That's how DNP3 SCADA ICS equipment is often referred to. And you're going to have this type of application is going to need an engineer to have visibility into a process. So you're generally going to have a human machine interface at some level where aggregated data is getting taken up to some server that is displayed in a graphic manner for a user, which is different from ICS, where it's just a device talking to another device. And then another interesting feature of DNP3 is it can go over Ethernet or serial communication, which typically, if you come from an IT background, considering you might have serial connections, is not even going to come up. So once again, where do you see this used? It's going to be used for high voltage. In Power systems, you're talking transmission and distribution at thousands of volts, tens of thousands, hundreds of thousands of volts, right? These are the applications where you're going to see DNP3 typically. In your lower voltages, down when you get into a neighborhood, or let's say at the panel or the meter at your house, this is not going to be something you're going to see there. And this is generally for a bunch of different reasons, which includes price of running communication lines everywhere, and also the decision, the logic for controlling the power system is typically going into substations. It's not going to be going all the way down to your house. You don't have something that the power system at large can control on the panel of your house. So you're not going to have a DNP3 connection there. So it's going to be high voltage connections, not low voltage connections. And part of the reason for this is it's a complex protocol, and you just don't need this level of control and complexity branching out to that level, right? So it's a highly configurable protocol with a lot of supported functions. What are all these functions? They let you read and write. They let you map items on the process to a specific integer value, a specific address in the protocol, right? So you might have a open breaker, a closed breaker, you might have a read a voltage, you have all these different things you can do. And data maps in the protocol are a thing that lets you control from another device that's using DNP3, what can I ask this device for? I can ask for a voltage reading, and I'm allowed to read that with any permission, right? You have the same style of permissions as you have in a Windows or Linux system. You have read and write attributes. So if I want to close or open a breaker, I might lock that down a bit more than just reading a voltage out of the device. But another thing that most people are not aware of if they are not in this world all the time is that just writing something to a device does not necessarily cause it to take action, especially when we're talking about dangerous actions. So if I have a power line that's taken offline because somebody needed to replace something, right? So it's a big thousands of volts power line that transfers lots of energy. I need to repair it. I take it offline. I have some guys out there working, and then I have a remote write that I am allowing through my data map, and it lets you write a close the breaker, so that turns the power back on. I'm going to have an interlock there that prevents that from just happening, right? There's going to be other logic in place. So let's talk about those interlocks. These interlocks are put in place by the engineers that design the system, right? So you have a substation controlling a bunch of power lines, and they want to make sure that people will not get hurt from electricity if at all possible. So they're going to put an interlock that says, I have 2 to 3 devices monitoring this line, and I might have a physical switch as well. So this physical switch is something that the engineers that are going to go work on this line are going to put in the unsafe position, right? So this is not safe to close this breaker in and turn the power on. I put it in the unsafe position, and I go work on the line. And let's say your new guy at the office sees the power off and goes, oh, customers aren't happy, this is off, and tries to close that breaker. Well, the interlock should receive the command to close the breaker. It's going to see that protection device 1 says, hey, this is not in a safe state. Protection device 2 says, hey, this is not in a safe state. And then the physical switch also will be in an unsafe state. So the breaker is going to reject the command, and it's going to log that, right? But let's say a mistake was made. So for some reason, these devices were misconfigured, and both of them say, hey, yeah, it's safe to turn the power back on. But these engineers have flipped this physical switch as well. Well, still, the output is based on this logical statement of input 1, 2, and 3 have to all be true before I'm going to close this breaker in. And so it's going to reject commands. This is one of the reasons that I've had to explain to many people in the past why having a close breaker command is not quite as dangerous as it sounds initially. If you're not familiar with these types of protocols, just being able to remotely send the command doesn't mean that I can open or close the thing. Interlocks might prevent this dangerous action. So some kid that hacks into your system and starts sending commands may not actually be able to do anything. Okay, so interlocks, right? They're primarily there for safety type things in power system, but in processes, you often have other reasons you're going to put an interlock in, right? If you have this complicated process that has a lot of inputs and outputs, you'll just put that logic into an interlock to make sure that the output can only take the correct choice. So you're going to write your logical equations based on your inputs and outputs, and everything should just work as long as your engineers have correctly devised your system. Also, timing will come into this a lot of times, and so you'll have some logic based on when you get the commands. Okay, so we talked about security briefly as it relates to interlocks, but that does lead into the other question that I've been asked many times, which is, well, this thing isn't encrypted, right? So everybody can just see your communications. Isn't that terrible? And you know, it probably is bad. It would be better if we encrypted for security, but there are many problems with that in SCADA and ICS systems. One of the biggest ones that is not well understood oftentimes is that encryption adds latency enough that it actually affects the safety of some of these systems. So to put this into perspective, let's say you're driving a car, you wreck your car into a pole that's holding up power lines, and these are high voltage lines, and these lines fall across your car, and now all of these devices have to exchange communications and decide to turn electricity off to this line. The way this happens is you detect the fault, and then you send commands, and the command gets to a breaker, and the breaker opens up the electrical connection, and the power turns off, right? So these breakers are rated typically in how many power cycles, 60 hertz cycles, it takes to open up that link. So let's say you have a breaker that says it will disconnect power, or a relay that will disconnect power in a single cycle of 60 hertz power. That's about 16 milliseconds, right? So you're saying that if I send you a command or if I detect the fault and send a command, you'll be turning off power in 60 milliseconds. But now I want to add encryption to that. Let's say that adds an extra millisecond or 2 or 3 of latency just to add the encryption and check the encryption on the other side before taking action, right? That's a fairly large percentage of that 160 hertz cycle, right? So we're talking easily adding another 20, 30, 40% of that delay just to add encryption. So if you have lots of power pumping through your car because you've wrecked into that pole, do you want the extra energy of those milliseconds pumping through your car, or do you want that power turned off quicker? That's the trade-off here, right? We can do some interesting calculations on how many joules are going into your car per millisecond, but that's math I'll leave to other people to bother with if you really care. But it turns out if it's a high voltage line, that's a lot more energy in those milliseconds. So that latency matters. Also, availability is affected by encryption, right? If I have to do key passing and my certificate has expired, or my key has been invalidated by some reason, and I send that open breaker command, and you go, oh, no, sorry, you're not activated, then that's going to be a problem. So ICS and SCADA Security have some interesting applications. Atypical of other communication links. So what can you do? Well, one of the things that people tend to not think of, once again, if you come from an IT background, is in SCADA and ICS, a lot of times you have a direct network link. So I have a fiber line going directly from this gateway to that gateway. And if I have a direct line, then you're not near so worried about this going over the internet and getting intercepted. You have limited session counts, right? If my device is only allowed to talk to one other device, then having you jump in and also give me commands is less of a concern. You have tightly controlled network boundaries, gateways and firewalls everywhere. These protocol maps, the data maps, those are another thing, right? If I am controlling what things you're actually allowed to do remotely by read and write permissions, then that prevents a lot of security issues. And then the interlocks that we talked about, those are a big part of how you enforce security on these links. But it is worth mentioning that DNP3 has a secure authentication sub-protocol. It's another layer of the protocol that you can do. Many devices don't support it because of the reasons I've mentioned here, but it is built into the protocol itself. It's just another layer. It adds a fair amount of complexity to the protocol. So I've not actually seen it in use, but it is a supported standardized protocol that you could implement in a device. It has some really cool features to it. It works over serial, which a lot of the encryption stuff that is built into Ethernet protocols just doesn't work on serial because it's not available. So that's one of the distinctions of the DNP3 secure authentication subprotocols. You can actually use it over these serial links as well. And just to mention OSI layers, because this is going to be relevant if you're looking at the protocol ever. The Open Systems Interconnect model, I believe that is. I don't have it written down in front of me, but this is a logical way of discussing how a protocol is laid out. And so just to give some more background of how these protocols work for people that need to have discussions later, you have 7 defined logical layers. These often don't map directly to standards or physical manifestations of these. These are just for discussing how the data gets packaged by a device. So for an example of application data, at the application layer, you have a voltage reading. So I tell you what's the voltage at that outlet, and it would read a voltage reading, right? And then at the transport data layer, the next layer there, you might have multiple readings all packaged together. So multiple voltage readings, maybe some current readings, right? And then the link layer is for packaging information about who's talking to who here. The physical layer can vary. This is where the serial versus Ethernet comes in. So once again, the typical use of DNP3 is just 3 layers. You can add that secure authentication layer and get 4 with session data as well. And just to also map out how this works in reality, if you have a transmit device with some really big data it's trying to send, the application layer says, here is a bunch of data. It passes it on to a transport layer, which says, oh, this is too big for me to send. So I'm going to give indexes and package these in another envelope. I'm going to stick the envelope of data you gave me, put it in a new one, and say which number this is. So you have 3 messages now. I'm going to mark this one as number 1 of 3, 2 of 3, 3 of 3. And then I'm going to pass it on to my next layer, the data link layer, glues on some header info. It says, hey, this is going from device 1 to 2, right? And then it sends it across that physical layer. And that could be serial or Ethernet. If it's Ethernet especially, there's a really good chance that those packets come in, those messages come in out of order. That's where the receiving layers will strip off each envelope, each address, each header info, and pass it on to the next layer. So the data link will get it first on the receive end and say, yep, this message is to me on device number 2, and it'll gather all those messages, hand them to the next layer. The next layer says, hey, these are out of order. It rearranges them, and it glues them together and passes them on to the application layer, and the application layer says, hey, I got some really big data, and processes it. So just as a discussion of how that works, hopefully that's useful. The hex is really just for people, they want to see what that means in reality oftentimes. And so it's useful to have, well, if you were to look at this data in a bytes capture and in hexadecimal, this is what that looks like. It's the same data I was just showing you, but real DNP3 traffic, right? So it looks like this. And then you could dive really deep into it and try to figure out what all of the individual bytes mean. But that's what something like Wireshark is for, right? And Wireshark will do that for you. Wireshark knows how to parse this data and will get the whole hierarchy into a nice tree view for you. So what do we talk about? SCADA protocols, what are they? It's a hierarchical protocol that is for device-to-device comms. It predates a lot of other protocols. Many other protocols do this and are useful in this world. However, there's pros and cons to any choice you make there. It incorporates a lot of cool features. Many of them are security related because that is a concern. You want to make sure your process is going to work reliably and securely. One of the features of DNP3 is that it works over Ethernet or serial, and it can be inspected by a lot of common Ethernet monitoring tools. That's all I've got for you today. I'm going to look at the chat real quick, see if anybody had any questions for me. All right, if no questions for me, I'm going to pass it on to David, and he'll talk about actual usage of this protocol. Oh. Yep, Wireshark will read DNP3 from a PCAP. I've done that many times. I don't know whether you'll have to decode it directly for the capture the flag here, though. I bet so. The standard, you really have to go to the standard, and that's some rough reading. I don't know if you've looked at protocol standards before, but this one's multiple PDFs and pretty technical.
Same answer.
Yeah, it's basically the same answer. You'd have to go get a copy of the standard. I believe it's, trying to remember if that one was free. A lot of them are behind paywalls. So your best bet is Wireshark for decoding DNP3. It really is going to be the easiest and quickest way to get started. It is a difficult protocol to parse by hand. I've had to do that before, and it's not fun.
Okay, so I'm going to be, my name is David Lowe. I work at the power group here at Infrastructure Defense at SEL. And I'm going to be talking about how to apply DNP3 in SEL devices. So how to configure the devices for DNP3 communications, as well as how we verify that it's working. So I'm just going to do kind of a walkthrough of how we set that up. So for this walkthrough, I'm going to be using an SEL-351 protection system. It's a SEL relay that you'd find in a substation. It's going to be the outstation device or the server, and it represents substation IED. Joe talked a little bit about IEDs earlier, and we're going to be sending some values, some binary and analog values from the 351 to the remote terminal unit, or RTU. And an RTU is pretty much the link between IEDs in, say, a substation to a larger SCADA system outside of the subsystem, or outside of the substation. And then we're also going to be receiving binary values from the RTU. And then the other device we're going to be using is the SEL-3530-RTAC, real-time automation controller. That's the client device, and it's going to be representing the RTU that we're communicating with. And it's going to be sending some binary values to the 351 and then receiving values from it. So the software we use to configure these devices, it's SEL proprietary software. At least the first two are. The first one is AcSELerator QuickSet, and we're going to use that to configure the SEL-351. And then AcSELerator-RTAC is used to configure the RTAC. And then we're also going to be using some terminal interface software to interact with the 351 to verify that DNP3 is working, and we're going to send, we're going to manipulate the 351 a little bit to send some signals to the RTAC. So in AcSELerator QuickSet, you open it up, you connect to the device, in this case, the 351, and you'll be able to see all the settings. So there on the left, you can see port 5. That's an Ethernet port that we're going to be using for DNP3. So we have to configure that port for DNP3 communications. So we have to set up the IP address. You can see in the square there on the left, the DNP ADR setting. That's really important. We're going to talk about that in a little bit. And then on the right, the screenshot on the right, we're going to configure the IP settings for the client device. So our RTAC. You can see that's in the Ethernet DNP master 1 setting on the list to the left. And then, so there are a lot of settings related to DNP3 in the 351. And they deal with various aspects of how the data is handled and how it's sent. And what's important right now when we're just setting it up are the DNP IP address for the client device and that REP ADR1, which is the address to report to, and the DNP session map. So those tell which DNP map we're going to be using, so which data we choose to send and receive, and which devices are going to be receiving and sending data. So these are those 3 most important settings: the DNP ADR, that's the DNP, not the IP address, but the DNP address for the 351. And then REP ADR1, that's the DNP3 address for the RTAC. And then DNP Map 1, that is the DNP3 map that we're going to be using to choose the data that we send and receive. For now, we can just leave all the rest of the settings. I think there's close to 20 different settings. So we can leave the rest as default. And I made up a document that gives descriptions of all the other DNP3 settings. So if you're interested in what all the other settings do, you can refer to that document. So Joe talked a little bit about DNP3 maps. So DNP3 doesn't carry metadata that describes the data that's being sent and received. So DNP3 maps are used to describe that data to the receiving and transmitting device. So it's a little confusing, especially when you're configuring the 351, but all of the outputs and inputs are from the perspective of the client device. So when we're setting up binary inputs on the SEL-351, we're actually setting up the binary values that we're sending from the 351 to the RTAC. So when you're looking at it from the 351 perspective, the inputs and outputs are reversed. So binary outputs are actually the values that are received by the 351 that are sent from the RTAC. And then analog inputs are analog values sent from the 351 to the RTAC. And then on the 351, there are also maps for analog outputs and counters, but for this demonstration, we're not going to be using those. So here's an example of what a DNP3 map looks like in the AcSELerator QuickSet software. So on the left, you have a list of categories of different relay word bits that you can select and put into your DNP3 map. And then in the middle, you have your relay word bit options. So all the relay word bits within that category. And then on the right are the actual mapped bits. So you see BI_000. The value for that DNP3 message is out 104, which is one of our output contacts on the 351. And so if you're not familiar, relay word bits are what SEL uses. They're binary values that we can use in, say, like a trip equation or other protection schemes. They basically define how we protect the system. So binary inputs, again, input to the SEL-RTAC, not the 351. So we're going to set one binary input, and like I mentioned, we're going to use out 104, and that's the status of one of our output contacts. And I specifically chose this one for this demonstration because we can use the terminal interface software to do the pulse command, which asserts the output for 1 second and then deasserts it. It's just a easily manipulated bit. Joe talked about dangerous actions. In general, manipulating a random output contact is not a good idea. But in this case, when I was setting up this presentation, I had the relay right next to me. I knew that output 104 was not connected to anything. So I knew it was safe. So in general, try to avoid manipulating output contacts when you can. So for binary outputs, we're going to map the binary value sent from the RTAC to relay or to remote bit 1. That's RB1. And these, like I mentioned, the remote bits are relay word bits that are received from external sources, and they can be used in protection and automation control equations. And that remote bit we're going to be able to manipulate from the RTAC. I'm going to demonstrate how to do that in a little bit. And then we're going to map one current and one voltage value. These are analog values, both with magnitude and phase angle. And so those are going to be our analog inputs to the RTAC. So now we can save and send those settings to the 351, and we're all finished with the AcSELerator QuickSet software, and we're moving on to AcSELerator-RTAC. So we're just gonna add a device, and you can see on the right there, we're gonna add a 300 series, a 351, and then DNP3 protocol. And then on the next pop-up window, you can see you decide what kind of interface you want. And in this case, we're gonna do DNP3 over Ethernet as opposed to serial. So here's all the communication settings. There's a number of them, but basically what we're going to do is match the settings that we put in our 351 and just move them over to the RTAC, and it should work. And then we can leave all the other settings as default for now. So now we have to map our inputs and outputs. So our binary input, this is the out 104 that we're sending from the 351. We're just going to click on that little plus icon at the bottom, add one input, and then we're going to use the little tag alias field. So we have like a human readable field that we can see and manipulate. And then binary outputs are set up in the same way. There's a few more fields here because they're fields that we can manipulate in the RTAC. They're not too important to worry about right now. But again, we're going to use the tag alias. We're just naming it binary out.status. And we're going to be able to manipulate that and then see what happens in the 351 to verify that it's working. And then we're going to add our analog inputs in the same way and label those through the tag alias field. So we can go, we have all our settings configured for the RTAC now, and we can take it online. And then we can go down to the little controller tab there on the bottom left. And then if we look at the message sent count and message received count, we should be seeing those incrementing. They should be going up depending on the poll settings that we set. When we set it up, we didn't really go over that, but we can set how often we want those poll messages to go out and send and receive data. So they should both be incrementing every few seconds. So that's good. We know our connection is good when those are incrementing. So first we're going to check our binary inputs. So we can click on the tags in the list there on the left, and then expand out our out 104 and look at the value. You can see on the far right, it says true there. But what we're going to do, usually it would say false because nothing is there. But when we use our terminal interface software and put in the out 104 command, that out 104 contact is going to assert for 1 second and then deassert. And so when that happens, we should be able to look in our RTAC software and see that ST value change from false to true for 1 second and then back to false. And so when that happens, we know that our binary inputs are working. So checking analog inputs, I had some voltages and current inputs on the 351. And so we can see that there's values in there for those. So we can verify that the analog inputs are working correctly. We have magnitudes and angles in there. So that's working well. And then checking binary outputs. So to do this, we're gonna again go to our terminal interface software on the 351, and we're going to, in the RTAC software, expand out and go to the operator latch on value and manipulate that to go to true. And then if we do the tar RB1 command that shows us the status of remote bit 1, that will change from 0 to 1 in the terminal interface software. So that's the way to verify that our RTAC is sending binary values to our 351. And that's how we set up and verify that DNP3 is working on the 351 and the RTAC. Are there any questions? I'll bring up the chat.